Sorry. How does this work? Where do I face? Okay, this is a breakdown. Okay, so this is a breakdown of the parameters you utilize to select your candidate. The first is producibility, where you look at the ability of your reservoir to produce hydrocarbons. Then frackability, like I mentioned, how can you pump into your formation? You need your geomechanical model, which is very important. You need your frac gradient, your barriers. And then the longevity, where you look at the production forecast and production curves. And then that's where you have your formula for the COS, the chance of success, where you weigh each of these properties against a normalized value. So you normalize the value and you weigh each of them. And then you add them up to get your chance of success. Then once you do this, you apply it to all your wells. For example, in this project, there were 20 wells that were looked into. And out of the 20 wells, you categorize them into different categories: Q1, Q2, Q3, and Q4. Under Q1, for example, that's the best scenario that this project has. There are about 7 wells under Q1. The rate is plotted against COS. So you have the highest section for your COS and your rate. That's why majority of the best wells are located in that quarter. So you pick the Q2. The QT is next, so 7, 2, and maybe pick one well from this, from the Q3, making them 10 wells. So 10 best wells were selected. Then looking at a case study for one of the wells, that's a vertical well for one of the candidate wells. You've got that has already produced from one of the zones. You see the lower zones is isolated. Sorry, this pointer is not working. The lower zones is isolated from the future plants that will be perforated above the bridge plug. So the target formation is in the oil-bearing 3261 sand, and in this case, only SP and resistivity logs was available. Because we don't have acoustic data on this well, we use synthetic data. We use correlations to develop a stress curve from density log. And then from the reservoir characteristics, you have your porosity to be 15, average water saturation to be 40%, and then permeability 27%. Then based on the stress profile that was developed from the density log, because we do not have acoustic data, we developed, as you can see there, but the thing is, you can also see that you have stress barrier. Stress barrier was caused due to depletion. The lower your
5 minutes.
Okay. The lower your pressures, the lower your stress. So you have like a stress barrier right there, which is good for your fracture, because it's going to help you contain your fracture. Then looking at production modeling, production was modeled using Prosper, and the best case we have for vertical lift pressure is 93.5 kg per cm square. Next, perform nodal analysis to get the maximum production, and this was 9.8 kiloliters per day based on inflow well characteristics. The next, also synthesized production based on different frac lengths, and there were indications of gains based on your nodal analysis, as you can see on the screen, from 2.6 to 9.9, based on different frac lengths, 50 meters, 100 meters, 200 meters, 300 meters. And then for reservoir engineering, because nodal analysis is 1D, reservoir had to do their own analysis to get a more dynamic result. And utilizing different frac lengths, they were able to obtain 4 times, to forecast 4 times the amount of initial, 2 times the amount of initial production. As you can see, the risk oil rate is twice the amount without hydraulic fracturing. So this one says that 52% of increment was obtained compared to 7 years of production from the same zone without hydraulic fracturing, meaning we have a very good candidate for hydraulic fracturing in this case. Based on the sensitivity analysis performed, you can see that for 50 meters, we have 8.1, 100 meters of frac length, 8.2, 200, 8.4. There's no need to perform hydraulic fracture up to 300 meters. 50 meters is all you need, because right there's no need. I mean, it doesn't make sense to waste money on 300 meters. And then based on the optimized frac length of 50 meters, hydraulic fracturing modeling was performed using MFrac, using the sonic log that we obtained, and an optimum frac schedule was generated. You can see a frac plot right here, and the half length generated was 100 meters, and conductivity is right there too on the screen. And this is what your geometry looks like after performing your modeling. So in conclusion, there's a comparative analysis performed to distinguish between this workflow and the traditional workflow. The new workflow is better in efficiency, accuracy, cost reduction, scalability, ease of implementation, and data utilization. And to conclude, there's better improved decision making, better resource optimization, and better scalability. Thank you. Any question?
First question from my side. What criteria you use for chance of success, and what should be the chance of success?
The criteria used for chance of success are pumpability, frackability, like I discussed, producibility, which is how well can your well deliver, how good can your well deliver, and longevity.
Depends on
how sustainable can your deliverability be. Yeah.
And what should be the chance of success for executing the frac job?
So it's based on the formula that, it needs to be weighed. Each parameter needs to be weighed against a normalized value. You need to normalize the parameters and also give them a weigh factor. So you multiply that together, add them up, and then you categorize them based on that.
Okay, thank you.
Yeah.
Floor is open for question.
Okay, Rahil Ahmed from United Energy Pakistan. My first question regarding the geomechanical analysis. You said through the density log, whatever the log you have available, you develop a geomechanical model. Then the question is how you calibrate that model with either through the, the breakouts in the hole or the data frag. Did you calibrate that? And the second question regarding the half length. The model, FAC model, it show you the multiple half length showing the rates, but in actual, how you, observe in actual after the job through the transient analysis, is there any difference in the design and the actual half length?
Come again with the second question.
Yeah, the second question regarding the half length or the fracture conductivity. In the design, you run the different sensitivities. But in the actual after the job, one way is to, through the net pressure matching you can find out, but what was the difference in the actual after the job through the transient analysis? Was there any difference over there?
Transient analysis.
The pressure transient analysis, when you perform the fracture and then you had the pressure transient analysis, you have some fracture, signature on the in the formation. So what was the difference compared to the design, which you designed through the frac model and now through the pressure transient analysis?
Okay, I get you. Okay, so to calibrate the data, you need to, one of the conditions is you need to have like offset data, like offset closure pressure around. If you don't, some of the wells we had to perform defeat analysis to calibrate. It's highly recommended if you don't have any offset data to perform defeat. From defeat, you can get your closure pressure, you can get probability, you can get pore pressure, right? Then again, there's a difference between the data you get in defeat and the data you get in your calibration test. Calibration test is more far field, defeat is near field, right? Because of the volumes that you pump. Then the difference between the design and, so in the design, it depends on the data you have. If you don't have good data, your data will be off. Your fracture conductivity will be off. You have actual data after you perform your fracture. I mean, because you've calibrated your stresses already. So definitely you expect the data to be different for the post-frac analysis.
Okay,
Good.
thank you.
Okay,
Nice presentation.
thanks.